Let yourself settle in right now. Find that position where your body feels held rather than tense, where your weight sinks down into whatever is beneath you, and nothing needs your effort. If you'd like to close your eyes, go ahead and do that. If you'd like to leave them open, let them go soft, unfocused, like you're looking at something that isn't quite there. Tonight, we're going somewhere that has called to human beings for as long as we have looked up at the sky and wondered. We're going to the closest star to our sun, and to the world that orbits it. A world that might look something like our own. A world that James Webb, the most powerful space telescope humanity has ever built, has now been turned toward. What it found out there, 4 light years from the warmth of our own star, changed the way scientists think about what we can know and what we might someday discover. But for now, there is nothing for you to do. There is nothing to solve, nothing to remember. Just breathe and let the universe come to you. Before we drift out among the stars, if this kind of content brings you a little peace, a little wonder, a little quiet joy at the end of your day, I'd love it if you'd consider subscribing to the Science Pillow and giving this video a like. It takes just a second, it means the world to this channel, and it helps us keep making these journeys together. Thank you, genuinely, for being here. Now, let's go. The nearest star is waiting for us. Section 1. Our nearest neighbor, the Alpha Centauri system. There is a star system so close to us that, in the grand scale of the Milky Way, it is practically our next-door neighbor. It lies in the direction of the southern constellation Centaurus, the Centaur, and on a dark, clear night in the southern hemisphere, it blazes with a soft, golden-white glow brighter than almost anything else in the sky. Its name is Alpha Centauri, and it holds within it 3 stars, a layered mystery, and at least 3 confirmed worlds, one of which sits in the exact zone where liquid water might exist on its surface. The Alpha Centauri system is a cosmic triple act. At its heart are 2 stars that orbit each other in a gravitational partnership so intimate it takes them about 79 years to complete a single dance around their shared center of mass. These 2 are called Alpha Centauri A and Alpha Centauri B, though in older star charts and among mariners of the southern hemisphere, they carry the names Rigil Kentaurus and Ptolemy respectively. Alpha Centauri A is the slightly larger of the pair, about 1.1 times the mass of our Sun and 1.5 times its luminosity. A warm, yellow-white star similar enough to our own that if you were standing on a world orbiting it, you might not immediately notice the star looked much different. Alpha Centauri B is slightly cooler and smaller, weighing in at about 90% of the Sun's mass and glowing at less than half its brightness, giving it a faintly more orange complexion. The 2 stars maintain a separation that varies over the course of their nearly 80-year orbit. At their closest approach, they pass within a distance roughly equivalent to the gap between our Sun and Saturn, and at their farthest, they spread out to nearly the same distance as Pluto to our Sun. From Earth, they appear so close together that through most binoculars they look like a single, unusually bright star. But the 3rd member of this family is the one that captures scientific imagination most powerfully today, and it is the one that matters most to our story. Its name is Proxima Centauri. It sits a little apart from the other 2, about 0.2 light-years away from the main pair, which in terms of the cosmic neighborhood is still close enough for the 3 stars to be gravitationally bound together, though the question of whether Proxima is truly a permanent bound member of the system or merely a long-duration captured companion has been debated by astronomers, The current best evidence suggests that Proxima Centauri does orbit the center of mass of the Alpha Centauri AB binary, completing one enormous, sweeping orbit that takes somewhere between 550,000 and 1 million years to complete. Proxima Centauri is where the real strangeness begins. It is a red dwarf, one of the most common types of stars in the entire universe. About 75% of all the stars in our galaxy are red dwarfs, those small, cool, dim, burning embers of nuclear fusion that glow with a ruddy, brick-red light. The most famous nearby ones include Barnard's star, Wolf 359, which some of you will recognize from a certain Star Trek battle, and, of course, Proxima itself. Red dwarfs are defined primarily by their low mass. Proxima Centauri contains only about 12.5% of the mass of our Sun, meaning it is barely above the threshold required to sustain hydrogen fusion at its core. It is only about 1/7 the diameter of the Sun, making it only about 50% larger than the planet Jupiter. Standing on a planet orbiting Proxima, you would look up and see something that barely deserved the name Sun by our standards. A dim, deep crimson disk hanging in a sky that would be shifted toward infrared light, painting the world in colors our eyes could only partially appreciate. And yet, despite its modesty in size and brightness, Proxima Centauri commands our attention above almost every other star in the sky for one simple, extraordinary reason. It is the closest star to the Sun. It sits at a distance of approximately 4.2 light-years, or about 25 trillion miles, from our own solar system. In the terms of our everyday experience, that might as well be forever. If you could board a commercial airplane and point it at Proxima Centauri, the journey would take about 5 billion years. The Voyager 1 probe, which humanity launched in 1977 and which has now crossed into interstellar space, would require more than 73,000 years to make the trip if it were pointed in that direction, which it is not. The fastest spacecraft ever launched by humanity, the Parker Solar Probe, would still need thousands of years to reach Proxima. The distances of space defy every intuition we have built up over our brief lives on the surface of one small planet. And yet, cosmically speaking, Proxima Centauri is our neighbor. If the entire Milky Way were scaled down to the size of a continent, our solar system and Proxima Centauri would be side by side on the same city block. The closest major galaxy to our own, the Andromeda Galaxy, would be on the other side of the world. Proxima's closeness, its accessible proximity in cosmological terms, is precisely what makes it so important and so tantalizing. Proxima Centauri was discovered in 1915 by a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg, South Africa. Innes was conducting a survey of stars near Alpha Centauri when he noticed a faint, reddish star that showed an unusually large proper motion, meaning it appeared to shift its position against the background stars at a measurable rate across time, a telltale sign of a nearby object. By measuring this proper motion and its parallax, the tiny annual shift in apparent position caused by Earth's orbital journey around the Sun, Innes calculated that this dim little star was in fact even closer to Earth than the magnificent Alpha Centauri pair. He named it Proxima Centauri, or Proxima from the Latin for nearest, making its name quite literally the nearest centaur, a poetic collision of ancient mythology and cold mathematics. For decades after its discovery, Proxima Centauri sat in astronomers' catalogues as a curiosity. The nearest star, yes, but also one of the most faint and ordinary-seeming objects in our celestial neighborhood. It was too dim to see with the naked eye. It produced no dramatic features visible to the instruments of its era. It was simply a small red point of light, the universe's closest lamp-post, unremarkable except for the accident of its address. But all of that changed dramatically in the summer of 2016. The universe, as it turns out, had been keeping a secret in the most obvious possible hiding place. Section 2. Discovering Proxima b, the pale red dot. To understand how we found a planet orbiting the nearest star, you have to understand something about the nature of planet detection itself, because we did not find Proxima b by taking a picture of it. We found it by listening to its star stagger. The technique is called radial velocity measurement, and it works by exploiting a beautiful consequence of Newton's laws of gravity. When a planet orbits a star, it is not simply the planet that moves. The star also moves. Pulled by the gravity of the planet in a small but real orbit around the two bodies' common center of mass. If the planet is massive enough and close enough, this stellar wobble becomes detectable through the Doppler shift it imprints on the star's light. When the star moves toward us in its tiny orbit, its light shifts slightly toward shorter, bluer wavelengths. When it moves away from us, the light shifts toward longer, redder wavelengths. By measuring these shifts in the star's spectral lines with extraordinary precision, astronomers can deduce the gravitational tug of an unseen planet. Its orbital period, the minimum mass required to explain the wobble, and clues about the shape of its orbit. For decades, astronomers had been scanning Proxima Centauri with various instruments hoping to detect exactly this kind of wobble. Early surveys in 2008 and 2009 had ruled out the existence of any large planets, anything bigger than a few Earth masses, in the star's habitable zone. But technology was improving rapidly, and a new spectrograph called HARPS, the High-Accuracy Radial Velocity Planet Searcher, attached to the 3.6-meter telescope at the European Southern Observatory at La Silla in Chile, was beginning to detect stellar wobbles measured in meters per second. That is the level of precision needed to find small, rocky planets. For context, the wobble that Earth causes in the Sun's motion amounts to about 9 centimeters per second, barely faster than a slow walking pace. HARPS was getting close to that level of sensitivity. Beginning in January 2016, a team of astronomers led by Guillaume Anglada Escudé of Queen Mary University of London launched a coordinated observing campaign they called the Pale Red Dot Project, a lovely tribute to Carl Sagan's description of Earth as a pale blue dot, now reimagined for the dim crimson light of Proxima Centauri. The campaign gathered data on Proxima's radial velocity using HARPS alongside simultaneous photometric monitoring to track stellar brightness. The goal was to cut through the noise of the star's own activity, its flares and star spots and chromospheric variations, all of which can mimic or mask the signals of planets, and find whatever might truly be lurking in orbit. The Pale Red Dot team worked quickly and somewhat urgently, because the closer you observe a star, the more time it takes to build up a statistically significant detection of a small planet's signal. By combining their new observations with archival HARPS data going back several years, they had amassed dozens of high-quality measurements of Proxima's radial velocity. The star's spectrum was examined for the characteristic periodic shift that would signal a companion's gravitational influence. And there it was. Hiding in the data was a signal with a period of 11.2 Earth days, meaning something was causing Proxima Centauri to rock back and forth with an 11-day rhythm. The amplitude of the wobble was small, about 1.4 meters per second, but it was real, consistent, and reproducible. The team ran rigorous statistical tests to exclude the possibility that it was caused by stellar activity, and the signal held up. They submitted their paper for peer review on June 9, 2016, and on August 24, 2016, the European Southern Observatory hosted a press conference that became one of the most widely covered science news events of the year. Guillaume Anglada Escudé stood before cameras from news agencies around the world and announced what the data was telling them. The nearest star to our Sun harbored a planet. The planet was given the name Proxima Centauri b, following standard exoplanet naming conventions that use lowercase letters starting with B for the first planet discovered in a system. It was only 4.2 light-years away. It orbited within the habitable zone of its star, and it appeared to have a minimum mass of about 1.3 times that of Earth, making it comparable in scale to our own planet. The scientific community's response mixed genuine excitement with carefully calibrated restraint. The discovery itself was thrilling. No one could deny that. A potentially rocky, Earth-like world in the habitable zone of the very nearest star was the kind of result that astrophysicists had fantasized about for generations. Carl Sagan had dreamed of it. Stephen Hawking had speculated about it. Science fiction writers had been placing stories there for decades. And now, with data from a spectrograph on a mountaintop in Chile, it had apparently become real. But the caution was warranted too. The radial velocity technique tells you only the minimum mass of a planet, because it cannot measure the inclination of the planet's orbit relative to our line of sight. If the orbit happened to be tilted, the true mass could be higher, potentially much higher, placing the object in a different category altogether. And importantly, the technique told us essentially nothing about the planet's actual surface, its atmospheric composition, its temperature, its color, or whether it had anything resembling conditions hospitable to life. We had detected a gravitational whisper. We had not seen the world itself. In the years following the discovery, astronomers worked steadily to refine and confirm the detection. In 2020, a new and even more precise spectrograph called ESPRESSO, the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations, attached to the European Southern Observatory's Very Large Telescope in Chile, was turned toward Proxima Centauri. After 63 separate observations, ESPRESSO confirmed the planet with measurements of even greater precision than HARPS had achieved. The mass was refined slightly, to a minimum of about 1.06 Earth masses, essentially Earth-sized, or perhaps just a tiny fraction more massive than our home. The orbital period remained 11.2 days. The planet's reality was no longer in question. And in 2022, astronomers announced the discovery of yet another world in the Proxima Centauri system. This one, called Proxima d, orbited even closer to the star than Proxima b, just about 4 million kilometers out, completing one orbit every 5.1 days. Proxima d is a genuinely tiny world, carrying a mass of only about 1/4 that of Earth, making it one of the lightest exoplanets ever detected through the radial velocity technique. Finding it at all required detecting a wobble in Proxima, Centauri's motion of only about 40 centimeters per second, the walking pace of a cautious toddler, over the vast light years between us and that small red star. In July 2025, the new Near-Infrared Planet Searcher, NIRPS, independently confirmed both Proxima b and Proxima d using observations in the infrared part of the spectrum, adding extra confidence to the planetary census. There is also a candidate third planet, given the designation Proxima c. It would be a hefty object, if it exists, with a mass somewhere around 6 times that of Earth, orbiting very far out with a period of about 5 years. But its existence is disputed. Follow-up observations have cast doubt on the signal that originally suggested it, and, as of 2025, Proxima c remains in an uncertain limbo, neither confirmed nor definitively ruled out. The investigation continues. It is worth pausing to appreciate what it actually took to find Proxima b in the first place. To measure a wobble of 1.4 meters per second in a star 25 trillion miles away. To place that measurement in context, 1.4 meters per second is roughly the speed at which a person walks slowly across a room. It is far slower than a car, vastly slower than an airplane, imperceptible to ordinary human senses. Yet astronomers detected this motion in the velocity of a star, translated into tiny shifts in the wavelengths of spectral lines collected by a telescope in the Chilean mountains, across a distance that light itself takes 4.2 years to cross. The precision required represents a triumph of engineering, optics, data processing, and basic physics that would have been considered science fiction barely 50 years ago. The man who led the discovery, Guillaume Anglada Escudé, spoke after the announcement with characteristic scientific honesty. He emphasized that the detection met all the statistical and methodological tests for a real planet, but that science always moves incrementally, that confirmation would come from future instruments, and that the uncertainty about Proxima b's habitability was vast. He knew, as all good scientists do, that the first discovery is only the beginning of the questions. So, the picture that has emerged from nearly a decade of painstaking work is this. The nearest star to our Sun hosts at least 2 confirmed planets, one of them tiny and scorchingly hot, and one of them Earth-sized, potentially rocky, and sitting in the zone where temperatures might allow liquid water. Whether that water exists, whether that rocky surface breathes the kind of air that any organism could use, whether life has found a way in this most accessible of cosmic addresses. Those are questions that burn with an intensity matched only by our extraordinary difficulty in answering them. Section 3. The nature of Proxima b, what we know and what we don't. When scientists speak of a planet in the habitable zone, they are using a term that requires careful unpacking, because it means something quite specific and somewhat limited. The habitable zone of a star, sometimes called the Goldilocks zone, refers simply to the range of orbital distances at which a planet with an Earth-like atmosphere and sufficient atmospheric pressure could maintain liquid water on its surface. It is not a guarantee of habitability. It is not an assessment of whether life could actually survive there. It is a statement about temperature and phase chemistry. At this distance, water would be neither entirely frozen nor entirely boiled away. Proxima b orbits its star at a distance of about 0.05 astronomical units, roughly 7.5 million kilometers, or about 4.7 million miles. That sounds extremely close to its star, and by the standards of our solar system, it is. Mercury, the innermost planet in our solar system, orbits at about 0.39 astronomical units from the Sun. nearly 8 times farther from its star than Proxima b is from Proxima Centauri. If you placed Proxima b in our solar system, it would be about 20 times closer to the Sun than Mercury currently is. But Proxima Centauri is not the Sun. It is a tiny, cool, dim red dwarf, radiating only about 0.17% of the energy our Sun puts out. For a planet to receive the same level of stellar warmth at this reduced radiation, it has to get dramatically closer. The numbers work out such that Proxima b, despite its extremely small orbital radius, receives roughly 70% of the energy per unit area that Earth receives from the Sun. Not far off from what we receive, and well within the range where liquid water could exist under the right conditions. The orbital period of 11.2 Earth days is a direct consequence of this tight orbit. Proxima b completes an entire year, one journey around its star, in roughly the time it takes Earth to go from a new moon to a waning crescent. The rhythm of seasons and years as we experience them would be completely alien on this world. There is another consequence of orbiting so close to a star, and it brings us to one of the most important and uncertain features of Proxima b: tidal locking. When a planet orbits very close to its star, the gravitational gradient across the planet's diameter creates a tidal force, pulling more strongly on the near side than the far side. Over long time scales, this differential tug slows the planet's rotation until it rotates at exactly the same rate as it orbits, so that the same hemisphere always faces the star. This is the condition the Moon is in relative to Earth. We always see the same face of the Moon because the Moon is tidally locked to our planet. Proxima b is almost certainly tidally locked to Proxima Centauri. Given the small orbital distance and the age of the star, estimated to be about 4.85 billion years, slightly older than our Sun, the tidal forces would have had more than enough time to synchronize the planet's rotation with its orbit. This creates a world of extraordinary extremes. The day side, permanently facing the star, would be bathed in constant red-tinged starlight, and could be heated to potentially scorching temperatures depending on the atmospheric conditions. The night side, permanently turned away from the star, would exist in eternal darkness, and could plunge to frigid cold. Potentially cold enough for gases to freeze out of any atmosphere and settle on the ground as ice. The region between these extremes, the terminator line, where day meets night in a continuous ring around the planet, has been the focus of some of the most intriguing climate modeling work for Proxima b. In this narrow band, temperatures might be moderate enough for liquid water to exist, creating what scientists sometimes call a terminator zone of potential habitability. Climate models suggest that if the planet has a substantial enough atmosphere with the right composition, atmospheric circulation could carry heat from the blazing day side toward the colder night side, moderating the extremes and potentially widening the habitable region. One scenario that has been modeled extensively is what researchers call eyeball Earth. A tidally locked planet with a roughly circular region of liquid water centered on the substellar point, where the star shines directly overhead, fading into ice toward the dark and frigid limb. In 2019, a team of researchers at NASA's Goddard Institute for Space Studies ran detailed three-dimensional climate models of Proxima b under a range of conditions, including different atmospheric compositions, the presence or absence of oceans, and varying amounts of salt in those hypothetical oceans. In almost all of their 18 separate simulation scenarios, Proxima b ended up with open liquid ocean persisting over at least some portion of its surface. The larger the fraction of the planet with liquid water, the better the odds that if there's life there, we can find evidence of that life with future telescopes, said researcher Anthony Del Genio. Even simulations with thin atmospheres and dry land-dominated surfaces produced pockets of liquid water. The minimum mass of Proxima b, about 1.06 to 1.3 Earth masses depending on which measurement you consult, is consistent with a rocky terrestrial world. This is not a gas giant or an ice giant. If its mass is close to the minimum estimated values, it most likely has a solid surface. Perhaps rocky and geologically active, perhaps bearing the chemical ingredients for complex chemistry. With an orbital inclination of about 47 degrees, estimated from the star's own rotation, the true mass has been calculated at about 1.44 Earth masses, making it a slightly larger cousin to our own planet rather than a true twin. But what does a minimum mass of 1.06 to 1.44 Earth masses actually look like in physical terms? Based on our knowledge of planetary composition, there are several possibilities. If Proxima b has an Earth-like composition, roughly a third iron core and 2/3 silicate mantle, its radius would be somewhere between 1.1 and 1.2 times Earth's. You would be standing on a planet slightly larger beneath your feet, with slightly stronger gravity, under a dim red sky. If it has more water or ice than Earth, which is plausible if it formed in a more volatile-rich zone and migrated inward, its radius could be larger, giving it a less dense interior and potentially global oceans. If it has less water and more iron, its radius would be smaller and its surface gravity higher. Each of these composition scenarios has profound implications for whether a geological engine capable of sustaining life could operate inside the planet. Earth's habitability depends critically on its active geology. Plate tectonics drives the carbon cycle that regulates our climate over millions of years. Volcanoes recycle carbon dioxide back into the atmosphere, and the motion of tectonic plates creates diverse environments that may have contributed to the origin of life. A world with too little internal heat would lose this engine quickly. But a world with slightly more mass than Earth would have more radioactive elements in its interior generating heat, potentially remaining geologically active for longer than our own planet. The presence or absence of a liquid iron outer core is similarly critical. Earth's geodynamo, the churning of liquid iron in our outer core that generates our global magnetic field, provides the planet's essential shield against the solar wind. Mars lost its magnetic field when its smaller iron core solidified, and the consequences were devastating. Proxima b, if it has retained sufficient internal heat and has a properly structured interior, could in principle sustain a dynamo, despite tidal locking. Theoretical work by Jorge Zuluaga and collaborators showed that thermally driven convection in a planetary core can generate meaningful magnetic fields, even without fast rotation, provided the planet is sufficiently massive and its mantle convection remains active. A planet twice the mass of Earth, even if tidally locked, might generate a magnetic field strong enough to stand off at least some of the stellar wind, though the geometry of the magnetosphere for a tidally locked world would be fundamentally different from Earth's. What we do not know about Proxima b forms a list that is, for now, far longer than what we do know. We do not know whether it has an atmosphere at all. We do not know its composition. We do not know its bulk density, which would tell us about the ratio of rock to iron to ice in its interior. We do not know whether it has a liquid iron core capable of generating a protective magnetic field. We do not know whether it has ever had oceans, or whether any liquid water it once possessed has long since been stripped into space. We do not know whether it has plate tectonics or volcanic activity that could replenish gases into an atmosphere. We do not know whether the chemistry of its surface could support anything resembling biology. All of these profound unknowns are not merely academic curiosities. They determine everything about whether Proxima b is a world capable of harboring life or a dead, barren rock blasted smooth by the relentless fury of its star. And the nature of that star, its activity, its temperament, its propensity for violence, turns out to be one of the most critical factors in the planet's fate. Section 4. The Fire and Fury of Proxima Centauri. The Flare Problem. Proxima Centauri is classified as a flare star. This designation tells you something important about the character of this particular red dwarf, something that makes it simultaneously fascinating and terrifying to contemplate as a life-giving sun. Flare stars are variable stars that can undergo sudden, dramatic, and unpredictable increases in brightness due to explosive events in their magnetic fields. Unlike our own sun, which releases energy in a relatively steady stream with occasional, somewhat predictable outbursts called solar flares, Proxima Centauri erupts with a ferocity that makes our sun's activity look almost polite by comparison. The mechanism is rooted in the star's interior structure. Unlike the sun, which has both a radiative interior and a convective outer layer, Proxima Centauri is fully convective, meaning that heat transport throughout the entire star happens through the physical movement of plasma rather than through radiation. Convection causes the hot plasma to circulate from the core to the surface and back again in a churning, turbulent motion. This churning twists and amplifies the star's magnetic field into intense, complex structures. When those tangled magnetic field lines snap and reconnect, releasing their stored energy in sudden explosions, the result is a stellar flare that can briefly increase Proxima's luminosity by factors of several. During calm periods between flares, Proxima Centauri's corona, the thin, hot outer atmosphere of the star, is already maintained at a temperature of about 3.5 million Kelvin, compared to the Sun's corona at roughly 2 million Kelvin. Even in quiescence, Proxima produces total X-ray emissions comparable to the Sun. But when it flares, the situation changes dramatically. The star's brightness can fluctuate by more than one magnitude in just a few minutes. Early photographic surveys showed that Proxima showed measurable brightness increases on about 8% of the survey plates, a remarkable frequency of activity that made it the most active flare star known at the time. On May 6, 2019, astronomers observing Proxima Centauri with 9 different ground and space-based telescopes, including the Hubble Space Telescope, the Atacama Large Millimeter/Submillimeter Array, and NASA's Transiting Exoplanet Survey satellite, witnessed a superflare of extraordinary magnitude. The flare event, lasting only a few minutes, caused Proxima Centauri to shine about 14,000 times brighter than normal in ultraviolet wavelengths. The energy released was roughly 100 times more powerful than the most powerful solar flare ever recorded from our own Sun. It was, at the time of its detection, the brightest flare ever recorded from Proxima Centauri, and among the most energetic ever detected from any nearby star in the Milky Way. What made this 2019 event particularly alarming from a habitability standpoint was not just its energy, but its spectrum. The flare released an enormous surge not only in visible light but in ultraviolet radiation and millimeter-wave radio emissions, wavelengths that are particularly damaging to biological molecules and atmospheric chemistry. A burst of ultraviolet radiation of that intensity, delivered to a planet's surface, could break apart the molecular bonds in DNA, destroy any ozone layer present, and strip away lighter atmospheric gases, and this is not a rare event. Proxima Centauri produces powerful flares on a regular basis. A study conducted by the Everscope telescope from January 2016 to March 2018 recorded 24 flares from Proxima with significant energies, suggesting that events reaching extremely high energies occur at least 5 or more times per year. The most powerful among these super flares are estimated to produce enough UV radiation to sterilize any unprotected surface within Proxima B's orbital radius. The stellar wind from Proxima Centauri, the continuous stream of charged particles blowing outward from the star, also bombards Proxima b, with dynamic pressures estimated to be up to 2,000 times stronger than what Earth experiences from the Sun. Proxima b receives 30 times more extreme ultraviolet radiation than Earth receives from our Sun, and 250 times more X-ray radiation, though this comparison needs to be understood correctly. These figures reflect the raw incoming flux at the planet's orbital distance. The Sun is more intrinsically energetic than Proxima in ultraviolet and X-rays, but Proxima b is so much closer to its star that the irradiation still adds up to a formidable assault. The implications for any atmosphere on Proxima b are sobering. Over billions of years, this continuous bombardment of high-energy radiation and stellar wind would work to erode atmospheric gases, particularly the lighter molecules like hydrogen and water vapor. The fate of Mars in our own solar system offers a sobering analogy. Mars once had a thicker atmosphere and liquid water at its surface, but over billions of years its global magnetic field shut down as its core cooled, stripping the planet of its atmospheric shield and allowing the solar wind to gradually scour away most of its air. Without a magnetic field to deflect the stream of charged particles, an atmosphere's days are numbered in cosmic terms. Whether Proxima b has a magnetic field capable of protecting it from this fate is one of the great open questions of nearby exoplanet science. The answer depends on factors we cannot yet measure: the planet's interior structure, its core composition, and, crucially, how fast it rotates. Tidal locking, as we discussed, is expected to have greatly slowed Proxima b's rotation. A slow rotation means weak magnetic dynamo action in the planet's core, which means a weaker magnetic field, which means less protection from stellar wind. The situation could be self-reinforcing. Slow rotation, weak shield, stripped atmosphere, barren surface. But here, the story gains some nuance and hope. Computer simulations published in 2024 in Astronomy and Astrophysics explored what happens to Proxima b's magnetosphere under both calm and extreme space weather conditions. If the planet has a magnetic field comparable in strength to Earth's own field, the models found that the planetary magnetosphere would be large enough to shield the surface from stellar wind across essentially all possible planetary orientations, except the most extreme tilt angles close to 90 degrees. Even under the violence of a simulated coronal mass ejection event, a planet with an Earth-like magnetic field remained reasonably protected. The catch, of course, is that if the planet has, we don't yet know whether it does. In 2025, new observations from the ALMA telescope array studied Proxima Centauri's flare activity in the millimeter wavelength range for the first time. The team, led by Kiana Burton at The University of Colorado found that Proxima's millimeter wave flaring was far more frequent than optical observations alone had suggested. The millimeter flaring seems much more frequent, said researcher Meredith McGregor. It's a different power law than what we see at optical wavelengths. If we only look at optical wavelengths, we're missing critical information. This new window on Proxima's activity reinforces just how complex and multifaceted its assault on any orbiting planets truly is. The ALMA study also found an intriguing asymmetry in some of Proxima's most powerful flares. The decay phase of these flares, the period after the initial energy release during which the flare's brightness fades back to the star's normal level, was substantially longer than the initial burst. This points to complex magnetic field processes that continue well after the first explosive reconnection event, suggesting that a flare is not a single discrete pulse of radiation, but rather a cascade of continuing activity in the star's atmosphere. For a planet like Proxima b, this extended decay means that the radiation environment after a major flare event remains elevated for longer than you might expect. Not a brief shock, but a sustained bombardment. The star's magnetic cycle adds yet another layer of complexity. Unlike the Sun's 11-year solar cycle, Proxima Centauri appears to cycle through periods of higher and lower activity with a period of only about 442 days, roughly 14 months. This means the star's flare rate and overall activity level varies significantly over timescales of just over a year. For any life hypothetically present on Proxima b, this cycling would create seasons of extreme radiation and seasons of relative quiet, potentially influencing the rhythm of whatever biological processes might try to establish themselves on or beneath the planet's surface. It's worth pausing here to let the full picture sink in. Proxima b is a world receiving, over its 4-billion-year history, doses of X-ray and ultraviolet radiation thousands of times greater than what Earth has received from our own relatively well-behaved Sun. Its star detonates with 100 times solar superflares on a regular basis, potentially multiple times per year. The stellar wind pressure at its orbit is 2,000 times stronger than what Earth experiences. Its likely tidal locking means it cannot rotate fast enough to generate a strong protective magnetic field. The early history of the system involved the habitable zone being in a completely different location, meaning the planet may have cooked in a runaway greenhouse phase before the star settled into its current routine. By any rational accounting, this is not a friendly environment for life, and yet here we are, unable to rule it out. That persistent inability to rule it out is itself a scientific statement. It reflects the genuine theoretical possibility that other factors might tip the balance, combined with our honest acknowledgement of how little we know about the planet's actual current state. The universe has surprised us before. The picture that emerges is one of a world under constant siege, living next door to a temperamental and unpredictable star that periodically unleashes fury on an astonishing scale. Whether life could survive or even thrive under such conditions is a question that touches on some of the deepest unknowns in astrobiology. But the universe rarely offers simple answers, and the story of Proxima b is far from over. Section 5. The question of an atmosphere. Survival against the odds. The atmosphere of a planet is its most precious possession. It is the thin, fragile envelope of gases that mediates between the vacuum of space and the surface, regulating temperature, protecting life from radiation, maintaining pressure, cycling water and carbon. Without an atmosphere, there is no weather, no hydrological cycle, no protection from the ultraviolet rays that shatter the molecular machines of biology. The question of whether Proxima b has retained an atmosphere is therefore the pivotal question around which its potential for life entirely turns. What we know from decades of climate modeling and stellar physics suggests that the answer is genuinely uncertain. Not in a disappointing, hand-waving way, but in the genuine scientific sense that the answer depends on initial conditions we cannot yet measure, and processes we are still quantifying. Let us begin with the bad news. When Proxima, Centauri, was young, perhaps in the first several 100 million years of its existence, it was far more active than it is today. Red dwarfs, somewhat counterintuitively, have long and violent youth periods, during which their activity is at its most extreme. Unlike the Sun, which settled into a roughly steady middle age within its first billion years, red dwarfs can sustain elevated levels of UV and X-ray emission for their first 1 to 2 billion years. During this period, Proxima Centauri would have bathed any orbiting planets in radiation levels dramatically higher than even today's already significant flare activity. There is an additional complication unique to the early history of the Proxima b system. When Proxima Centauri first formed and was in its pre-main sequence phase, burning brighter and hotter as it contracted toward its final stable configuration, the star's habitable zone was in a very different place. Computer modeling suggests that Proxima b, in its current orbit, would actually have been too close to the star during this pre-main sequence phase, receiving too much energy for water to remain liquid, and instead experiencing what is called a runaway greenhouse effect, similar to what happened to Venus in our solar system. Under a runaway greenhouse, temperatures climb until all surface water evaporates into steam, and the water vapor then gets broken apart by UV radiation into hydrogen and oxygen. The hydrogen escapes to space, the oxygen may oxidize surface rocks, and the end result is a planet that has lost its water inventory before any stable life could have taken hold. Whether this early catastrophe actually occurred on Proxima b depends heavily on when and how the planet formed, and whether it might have continued to receive water delivery from asteroid and comet impacts over billions of years. A process that likely resupplied our own Earth with much of its ocean water after the initial formation period. The universe, as always, offers multiple pathways. Now for the nuanced middle ground. Even in the current epoch, with Proxima Centauri's activity at its lowest point in the star's history, the stellar wind pressure at Proxima b's orbit is extreme by any measure. MHD, magnetohydrodynamic, simulations of the Proxima system have shown that the stellar wind dynamic pressure at Proxima b can be up to 3 orders of magnitude higher than what Earth experiences from the Sun under typical solar wind conditions. In the most severe CME events, these pressures increase further. But what the same simulations also show is that atmospheric escape is not inevitable if the planet has retained sufficient internal heat to drive geological activity. A planet that is geologically active, with volcanoes outgassing CO2, water vapor, and other molecules into the atmosphere, could theoretically replenish what the stellar wind strips away. The balance between atmospheric loss and replenishment may be the decisive factor. On Mars, loss eventually won. On Earth, it has not. Where Proxima b falls on this spectrum is unknown. There is also the possibility that tidal locking, rather than simply being a death sentence for an atmosphere, might allow for a complex and interesting climate regime. The perpetual temperature gradient between the blazing day side and the frigid night side creates powerful atmospheric circulation patterns, with winds driving heat from the substellar hemisphere toward the dark side. Climate models that include dynamic, circulating oceans have found that in many scenarios, the combination of atmospheric and oceanic heat transport can produce a planet with open liquid water maintained not just in the substellar eyeball region, but spreading through the equatorial band and potentially covering significant fractions of the surface. Even though the night side never sees any starlight, there's a band of liquid water that's sustained around the equatorial region, explained Planetary scientist Anthony Del Genio. The composition of any atmosphere would matter enormously. A thick CO2-dominated atmosphere would create a powerful greenhouse effect, keeping the planet warm on both the day and night sides. But CO2 buildup could also potentially reach toxic concentrations. And on Earth, the carbonate-silicate cycle regulates CO2 over geological timescales through weathering reactions. Whether a tidally locked planet with potentially very different patterns of rainfall and rock exposure could sustain this cycle remains an active area of research. A nitrogen-dominated atmosphere similar to Earth's would create different conditions. Nitrogen is relatively inert. It doesn't interact strongly with stellar radiation in ways that would cause rapid atmospheric escape, and its greenhouse contribution is modest. A planet with Earth-like nitrogen and water vapor could potentially maintain moderate surface temperatures across a significant fraction of its surface, depending on atmospheric thickness and circulation patterns. One of the more intriguing specific possibilities explored in climate models is what happens to Proxima b if it has an ocean. Oceans are remarkably efficient heat transporters. They can carry thermal energy from the substellar hemisphere to the dark side far more effectively than the atmosphere alone. Models that include both oceanic circulation and atmospheric dynamics find that a planet with a deep global ocean, even if tidally locked, can develop a climate significantly warmer and more uniformly distributed than a land-dominated world. Ocean worlds around red dwarfs might actually be among the more hospitable categories of planet, precisely because water's high heat capacity and its ability to circulate globally helps smooth out the brutal temperature extremes that tidally locked land worlds would otherwise experience. One intriguing finding from several independent climate studies is that the specific spectral quality of Proxima Centauri's light, redder and more infrared heavy than sunlight, lacking much of the blue and ultraviolet component, might actually interact differently with potential atmospheric photochemistry than our own sun's spectrum. UV radiation on Proxima b would be proportionally less intense in certain wavelength ranges, which might reduce some forms of photochemical atmospheric destruction. On the other hand, the same red-heavy spectrum means that standard oxygen-producing photosynthesis, which relies on red and blue light in roughly equal measure, would be less efficient. Any photosynthetic life on Proxima b would need different biochemistry, perhaps using the infrared wavelengths that Proxima provides abundantly, leading to hypothetical organisms that would appear nearly black to human eyes, maximally absorbing every photon of the red starlight available. The very nature of a day on Proxima b, if the planet is tidally locked, would be radically different from what we know. There would be no sunrise and no sunset in the traditional sense. The substellar point, the spot on the planet's surface where the star hangs directly overhead, would experience permanent noon. Every other point on the day side would see the star fixed at some angle in the sky, never moving. The terminator region, where day and night meet, would experience a permanent twilight, the star perpetually on the horizon. The night side would know nothing but stars, the full glory of the Milky Way blazing overhead for all of geological time. What would it be like to stand on the terminator of Proxima b, if somehow you could get there and breathe its air? Proxima Centauri would be hanging at the horizon, a dim red disk about 3 times the apparent diameter of our Sun, but emitting its energy much more in infrared light than visible. The sky around it might glow in shades of copper and rust. Behind you, the permanent night would be impossibly clear. No day-night cycle to give. The stars their daily rhythm, just a frozen sky full of points of light. Among them, a faint yellow star in the direction of what they would call the northern sky, 4 light years away, the star our civilization calls the Sun. All of this theoretical complexity resolves into a single, profound observation. We do not know. And the way we will find out is with instruments of extraordinary sensitivity pointed at this extraordinary target. Which brings us, finally, to the James Webb Space Telescope. Section 6. James Webb comes to the neighborhood. What it did and found. The James Webb Space Telescope was launched on Christmas Day, 2021, perched atop an Ariane 5 rocket from the Guiana Space Center in French Guiana. It deployed its sunshield, mirror segments, and scientific instruments over the following weeks with a precision that moved many of its engineers to tears, or at least to expressions of profound relief, and arrived at its operating position at the Sun-Earth Lagrange, about 1.5 million kilometers from Earth, where it has remained ever since, watching the universe with its great golden eye. Webb is, by any measure, an extraordinary machine. Its primary mirror is 6.5 meters across, composed of 18 hexagonal gold-coated beryllium segments that were precisely aligned to within nanometers of their target positions. The mirror's area is more than 6 times larger than Hubble's, giving Webb a light-gathering power that dwarfs its famous predecessor. But even more important than its size is its spectral specialty. Webb was designed to observe primarily in the infrared, in wavelengths of light longer than visible red, where the heat signatures of distant galaxies, newborn stars, and cool exoplanet atmospheres glow most clearly. Infrared astronomy is extraordinarily powerful for exoplanet science. When a planet transits its star, crosses in front of the star as seen from Earth, some of the starlight passes through the planet's atmosphere on its way to our telescopes. The atmosphere's molecules absorb specific wavelengths of this starlight, leaving their chemical fingerprints on the star's spectrum. By analyzing these absorption features, astronomers can, in principle, identify the molecules present in the atmosphere. Carbon dioxide, water vapor, methane, oxygen, ozone, each with its own distinctive spectral signature. This technique is called transmission spectroscopy, and Webb's infrared sensitivity and spectral resolution are perfectly matched to it. In its first years of operation, Webb has already detected carbon dioxide in the atmospheres of several transiting exoplanets, detected water vapor in others, and tantalizingly found possible traces of dimethyl sulfide, a molecule associated with biological processes on Earth in the atmosphere of a sub-Neptune called K218b, about 120 light-years away. But Proxima b poses a unique and frustrating challenge for transmission spectroscopy. The planet is almost certainly not transiting. For a transit to be observable, the planet's orbital plane must be aligned within a very narrow range of angles relative to our line of sight. Essentially, the planet must pass directly in front of the star from our perspective. Given Proxima b's orbital geometry, the probability of it transiting is estimated at less than 2%. Observations from multiple campaigns have found no evidence of transits, and the general scientific consensus is that we will never be able to use transit spectroscopy to study Proxima b's atmosphere, if it has one. This leaves direct imaging as the primary avenue, and it is here that Webb has been making remarkable strides, and where the recent news from the Alpha Centauri system has set the scientific community buzzing with cautious excitement. Direct imaging of exoplanets is among the hardest things astronomers attempt. A planet next to a star is like trying to see a firefly sitting next to a lighthouse from 30 kilometers away. The star's light overwhelms the planets by factors of many thousands, sometimes millions. To overcome this, astronomers use coronagraphs, devices that block the star's blinding light using precisely shaped masks placed in the optical path, allowing the much fainter surrounding region to be studied. Webb is equipped with coronagraphs in both its near-infrared camera and its mid-infrared instrument, or MIRI. It was MIRI's coronagraph that played the starring role in the most significant recent observations of the Alpha Centauri system. In August 2024, a team of astronomers led by Charles Bachman of NASA's Jet Propulsion Laboratory and PhD student Aniket Sanghi of the California Institute of Technology pointed Webb's MIRI coronagraph at Alpha Centauri A, not at Proxima Centauri itself, but at the larger sun-like star of the system. This was an observation that Bachman had been arguing for since 2017, years before Webb even launched. He had sent emails to colleagues proposing that Webb might be sensitive enough to directly image planets in the habitable zone of Alpha Centauri A, an ambition that many considered technically impossible, given that the system's binary companion, Alpha Centauri b, adds additional unwanted light right where you're trying to look. The team developed a novel observational strategy to deal with the binary challenge. They used Alpha Centauri b itself, the bright companion star, as a reference to subtract out the point spread function of the optical system. By subtracting both stars' light contributions from the images, they hoped to reveal anything lurking nearby that was far fainter than either star. When they processed the data from August 2024, they found something they had not quite expected to see so clearly. Emerging from the subtracted images at a statistical significance of about 5.5 sigma, a threshold most physicists would call a detection, was a faint point source of light. They labeled it S1. Its position placed it at roughly twice the Earth-Sun distance from Alpha Centauri A. Its brightness in the mid-infrared, at a wavelength of 15.5 micrometers, was consistent with what a gas giant planet might emit. Something roughly the mass of Saturn, perhaps, or possibly Jupiter. If it was a planet, it would be the closest planet ever found orbiting in the habitable zone of a sun-like star. As a direct imager, you're always confounded by artifacts, Sanghi said. You're very skeptical of anything you see, but this one just popped out so clearly. The team spent months trying to destroy their own detection, testing whether S1 could be an instrumental artifact, a background galaxy, or stray light from a known source. None of the alternative explanations quite fit the data, but confirmation would require seeing the object again at a different orbital position. In February 2025 and again in April 2025, using director's discretionary time, the reserved portion of Webb's schedule for urgent or high-impact observations, the team looked again. S1 was gone. The faint blob that had appeared so clearly in August 2024 was absent from the later data. "We are faced with the case of a disappearing planet," said Sankey. Rather than giving up, the team turned to computer modeling. They simulated millions of possible orbits for S1, incorporating the known constraints from the original detection and from the non-detections in 2025. They found that about half of the stable orbits that fit the August 2024 astrometry would also be consistent with the planet having moved to a region behind the coronagraph, too close to the star to be detectable, in the February and April observations. The planet, if real, would be in an elliptical orbit that swings between roughly 1 and 2 astronomical units from Alpha Centauri A. The team also looked at an earlier observation from 2019, taken with the European Southern Observatory's Very Large Telescope, that had hinted at a similar source near Alpha Centauri A, but had never been confirmed. Combining that potential earlier detection with S1 as a possible single object moving through an elongated orbit, the orbital simulations produced plausible scenarios that fit all the data: the 2019 hint, the 2024 detection, and the 2025 non-detections. We found that in half of the possible orbits simulated, the planet moved too close to the star and wouldn't have been visible to Webb in both February and April 2025, Sankey explained. The scientific community has responded with a mix of genuine excitement and appropriate restraint. "If it's real, it's amazing," said Elizabeth Matthews, an exoplanet astrophysicist at the Max Planck Institute for Astronomy in Heidelberg. "It's a really exciting candidate, quite an intriguing candidate." The authors work hard to make a case for why this, frankly, small and faint blob of light is believable, but I think there are still some open questions. Emily Rickman of the European Space Agency noted that even if this ultimately is a non-detection and the planet candidate is something else, it's a really important paper in understanding the true capabilities that JWST's MIRI can push to. What does all of this mean for Proxima b? Directly, the recent JWST result involves Alpha Centauri A, a different star in the same system, and not Proxima Centauri's planet. But the significance for Proxima b is nonetheless profound and multi-layered. First, it demonstrates that Webb can detect faint objects in the habitable zones of the nearest Sun-like stars through direct imaging, something that was considered at best technically extraordinary and at worst impossible before 2024. The techniques developed for Alpha Centauri A, including the binary star reference subtraction method, could potentially be adapted for Proxima Centauri observations. Second, researchers have already performed detailed simulations of what Webb's MIRI coronagraph could potentially do if aimed at Proxima Centauri itself. Published in November 2025 in an Earth.com covered study, a research team built detailed simulations of using MIRI's coronagraph to search for planets around Proxima Centauri, in the range from about 0.2 to 0.5 astronomical units, a region that includes and extends just beyond the habitable zone. They modeled planets at temperatures of 250 Kelvin, 400 Kelvin, and 600 Kelvin, covering the range from Earth-like warmth to somewhat hotter, and found that planets in the warmer part of this range could in principle be detectable, though the challenge of subtracting Proxima Centauri's own light remains formidable. Third, the very fact that Webb was turned toward the Alpha Centauri system at all, that it was deemed a scientifically worthy expenditure of the telescope's precious time, reflects a broader shift in the community's assessment of what can be accomplished with direct imaging in our stellar neighborhood. Every successful observation, every technique refined, every piece of software developed for processing coronagraphic images in the presence of binary star contamination, is a building block toward the eventual direct imaging of Proxima b. And there are future instruments on the horizon that are specifically designed with this goal in mind. A project called Ristretto, being developed by researchers at the University of Geneva, is a high-precision spectrograph designed to be mounted on the European Southern Observatory's extremely large telescope. The 39-meter behemoth currently under construction in the Chilean Atacama Desert. Simulations of Ristretto's performance have shown that it should be capable of directly detecting reflected light from Proxima b and searching for atmospheric signatures including oxygen and water. The instrument prototypes have already been successfully tested, and early results are encouraging. The extremely large telescope is expected to see first light in the late 2000s. Meanwhile, NASA's Nancy Grace Roman Space Telescope, planned for launch by May 2027, carries visible light coronagraphic technology that would complement Webb's infrared capabilities for exoplanet characterization in the Alpha Centauri system. We are not yet looking directly into the eyes of Proxima b, but we are getting closer. The instruments are being sharpened. The techniques are being refined. The photons are beginning to tell us their secrets. There is one final, quietly remarkable thing to say about what James Webb has contributed to the neighborhood of Proxima Centauri, and it has to do not with the question of what we see, but with the question of what we can rule out. The deep coronagraphic sensitivity achieved in the Alpha Centauri observations, reaching contrast levels of about 100,000 to 1 at separations greater than 1 arcsecond from the star, sets meaningful upper limits on what kind of objects could be present and undetected in the system. Any planet substantially brighter than what Webb would have detected is now excluded. This kind of negative result sounds anticlimactic, but in science, knowing what is not there is just as informative as knowing what is. It tightens the prior probabilities. It constrains the models. It tells the theorists which parts of their parameter space are no longer available. And every constraint, every reduction of uncertainty, is a step toward the answer. The search for Proxima b's atmosphere and the search for life on Proxima b are perhaps the most important scientific journeys of the coming decades. They will be long, demanding, and at times frustrating. But they have begun. Section 7. The full planetary system. Proxima d and the remarkable census of our nearest neighbor. The story of the Proxima Centauri planetary system has evolved substantially since the initial excitement of 2016. What began as a single tantalizingly Earth-like world has grown into an emerging picture of a compact, multi-world solar system right on our cosmic doorstep. The smallest confirmed planet in the system is Proxima d, and it has a story worth telling in its own right. Its discovery was an achievement of extraordinary instrumental precision. The first hints of it appeared in radial velocity data from the espresso spectrograph in 2020, as part of a study refining the mass of Proxima b. Astronomers noticed a weak 5-day signal buried in the stellar noise, far too small to identify confidently with earlier instruments, but just barely visible to espresso's exquisite sensitivity. The team, led by João Faria at the Instituto de Astrofísica e Ciências do Espaço in Portugal, formally proposed Proxima d as a planet candidate in a paper published in February 2022 in Astronomy and Astrophysics. Proxima d is a sub-Earth. Its minimum mass is about 0.26 Earth masses, about a quarter of our planet's mass, roughly twice the mass of Mars. To put that in physical terms, if it has an Earth-like rocky composition, it would have a diameter somewhere around 0.8 to 0.9 times Earth's, smaller than our planet but still comfortably in the terrestrial category. It orbits at a distance of about 4 million kilometers from Proxima Centauri, even closer than Proxima b, completing one orbit every 5.1 days. At this distance, it is well inside the inner edge of the habitable zone, receiving far too much stellar flux to maintain liquid water on its surface under any plausible atmospheric conditions. The gravitational effect Proxima d has on its star is almost imperceptibly small. Its presence is betrayed by a wobble in Proxima Centauri's motion of only 40 centimeters per second, roughly walking pace. Measuring this signal required not only the extreme precision of espresso, but meticulous modeling of the star's own activity signals to prevent them from masking or mimicking the planetary signature. This achievement is extremely important, said Pedro Figueira, Espresso's instrument scientist at the European Southern Observatory. It shows that the radial velocity technique has the potential to unveil a population of light planets, like our own, that are expected to be the most abundant in our galaxy. The confirmation of Proxima d came in July 2025, when the Near-Infrared Planet Searcher, NIRPS, achieved an independent detection of the 5.12-day signal in the infrared part of the spectrum. Led by Alejandro Suárez Mascareño of the Instituto de Astrofísica de Canarias, the team obtained 420 high-resolution infrared spectra of Proxima Centauri over 159 nights between 2023 and 2025, producing 149 precise nightly radial velocity measurements with sub-meter per second precision. The result not only confirmed Proxima d, but also refreshed and refined the parameters of Proxima b, giving the system's basic architecture a new level of measured confidence. The NIRPS team also found inconclusive evidence for the controversial Proxima c candidate, the putative super-Earth on a 5.2-year orbit. They could neither confirm it nor definitively exclude it, leaving the question open for future work. The fact that it remains debated after years of observation reflects both the difficulty of distinguishing real, long-period planetary signals from the complex variability patterns of active red dwarf stars and the general challenges of exoplanet science at the frontier of detection capability. What the Census looks like in 2025, with our best current knowledge, is this. Proxima Centauri has 2 confirmed planets. The inner one, Proxima d, is a sub-Earth approximately twice the mass of Mars, orbiting every 5.1 days on a scorchingly hot path that places it far too close to the star for habitability. The middle one, Proxima b, is an Earth-sized world of at least 1.06 Earth masses, orbiting every 11.2 days in the tepid middle ground, where water might, under the right conditions, remain liquid. A third candidate, Proxima c, is possible but unconfirmed. No other planets have been detected in the system, and the NIRPS analysis found no evidence for additional inner companions more massive than about 0.15 Earth masses within orbital periods of 10 days. The separation between Proxima d and Proxima b is only about 0.02 astronomical units. They are closer together in orbital space than any two planets in our own solar system, bound in a compact architecture around a cool red star. The gravitational interactions between them, while subtle given their small masses, could potentially have interesting effects on the orbital evolution of both worlds over astronomical timescales. In a touching parallel to the planet's story itself, the two confirmed planets around Proxima Centauri have the unique distinction of being the closest exoplanets to the solar system. Every other star system we know of is farther away. Proxima b and d are our nearest confirmed planetary neighbors in the universe. And yet they remain profoundly alien and unknown to us, separated by a gulf that all of human technology cannot yet meaningfully bridge. There is something both humbling and motivating in that. The nearest worlds beyond our solar system are tantalizingly close by cosmic standards, and yet even they demand instruments, patience, and ingenuity at the absolute frontier of what human science can achieve. The history of Proxima b is in many ways the story of how hard it is to know anything about another world, and also, simultaneously, a testament to how far we have come. Section 8. The Dream of Going There. Interstellar Ambitions and Breakthrough Starshot. Among all the things that Proxima b's discovery has inspired, perhaps the most audacious is the genuinely serious scientific discussion it sparked about one day sending a physical probe there. Not in some distant, speculative, hand-waving way, but with real money, real engineering, and a real timeline measured in decades rather than centuries. The initiative is called Breakthrough Starshot, and its story is one of spectacular ambition colliding with the formidable reality of physics and engineering. It was formally announced in April 2016, in the same year that Proxima b was confirmed, which is probably not entirely coincidental. At a press conference in New York attended by the late Stephen Hawking, physicist and cosmologist Yuri Milner, and Facebook founder Mark Zuckerberg. Milner pledged $100 million as seed funding for a proof-of-concept research program with a simple but staggering goal: develop the technology to send a fleet of tiny spacecraft to the Alpha Centauri system within a generation. The fundamental concept of breakthrough starshot is elegant in the way that truly audacious ideas sometimes are. You cannot propel conventional spacecraft to the speeds needed to reach another star in any reasonable time frame. With current chemical rockets, the journey would take tens of thousands of years. But light carries momentum. If you could build a sail light enough and reflective enough, and if you could focus an enormously powerful laser beam on it, you could accelerate the sail to a substantial fraction of the speed of light within minutes of exposure. At 20% of light speed, the journey to Proxima Centauri would take only about 20 years. A message confirming arrival would take another 4 years to travel back to Earth. An entire round trip of information could be accomplished in under 25 years from launch. The spacecraft, envisioned for Starshot, are called starchips. Tiny, gram-scale wafers of electronics, instrumentation, and circuitry attached to gossamer-thin sails made of engineered reflective materials, perhaps just a few hundred atoms thick. Each starchip would carry cameras, spectrometers, and communication lasers. A fleet of perhaps 1,000 of them would be launched together, compensating for inevitable losses due to interstellar dust collisions and technical failures. The laser array needed to push them, delivering tens of gigawatts of focused power to the sails during the brief acceleration burn, would be a multi-kilometer installation on Earth or possibly in space, representing an engineering project without precedent in human history. What happens if a starship reaches Proxima b? Traveling at 20% of light speed, it would flash past the planet in a matter of seconds to minutes, far too fast to stop or orbit. But in those seconds, with cameras capable of resolving features tens of kilometers across on the planet's surface, it could capture images and data that would transform our understanding of the world utterly. We would see surface features. We would measure atmospheric composition through infrared spectroscopy. We might detect the presence of oceans, ice, clouds. We might find evidence of biological activity, or perhaps the absence of it. The data would take 4 years to arrive back on Earth, but it would arrive, the first physical reconnaissance of another world orbiting another star. The technical challenges are extraordinary. Among the 30 or so distinct engineering problems that the breakthrough Starshot team identified at the outset, the most daunting include building a ground-based laser array capable of producing gigawatts of coherent power and steering it with milli-arc-second precision. Engineering sail materials that can survive being illuminated by these enormous laser intensities without vaporizing. Building chips that can survive decades of exposure to the interstellar medium, including dust, cosmic rays, and radiation, while remaining operational, and developing a communication system that can beam data back across 4 light years, using only the tiny power available on a gram-scale chip. There has been real research on these problems. Laser propulsion expert Philip Lubin at the University of California, Santa Barbara published a foundational roadmap for interstellar flight that provided the conceptual backbone for Starshot. Teams at institutions from Caltech to MIT to the Australian National University worked on specific technical challenges. Light sail materials were developed with impressive reflective properties. Tiny chip designs were explored. The project attracted genuine scientific talent and produced legitimate research papers. But by 2025, the trajectory of breakthrough Starshot had become uncertain. A report published in Scientific American in September 2025 documented what appeared to be an indefinite pause in the project's momentum. Total documented spending was estimated at only about $4.5 million across roughly 30 contracts, a fraction of the original $100 million pledge. Large meetings had given way to smaller ones, which had then given way to silence. The immense scale of the required laser array, the unsolved communication problem, and the sheer cost of making the concept work at the required level of precision had, it seemed, encountered the same wall that confronts all revolutionary engineering. The gap between inspiration and implementation is enormous, and closing that gap costs more in time, money, and solved problems than early enthusiasm can sustain. This does not mean the dream is dead. Several smaller-scale interstellar exploration concepts continue to be discussed, including NASA Innovative Advanced Concepts grants exploring swarm missions to Proxima Centauri. The underlying physics of laser-propelled light sails is sound. The concept works in principle. It's the engineering that remains to be conquered, and the history of aerospace is full of ideas that seemed impossible until someone found a way. Meanwhile, even if breakthrough Starshot never launches, it has already accomplished something valuable. It has made the interstellar probe a serious topic of scientific and engineering discussion. It has prompted researchers to think rigorously about what instruments you would want aboard such a craft, what data you would need to collect to answer humanity's deepest questions about Proxima b, and what level of technological maturity is genuinely required. In doing so, it has sharpened the scientific community's articulation of what they most urgently want to know about our nearest planetary neighbor. The fact that we take seriously the idea of sending spacecraft to another star in decades rather than centuries says something profound about the historical moment we inhabit. It is, in its way, the most hopeful possible response to the discovery of Proxima b, an acknowledgement that proximity matters, that the nearest world is worth reaching toward, and that the human impulse to go and see for ourselves has not diminished with the scale of the challenge. Section 9. What it all means. The cosmic question. Proxima b has become, in the decade since its discovery, something more than a data point in an exoplanet catalog. It has become a mirror, a way of asking questions about our own existence, our significance, and our place in a universe that stretches beyond all imagination. Consider what it would mean if life were discovered on Proxima b. Not intelligent life, not cities or radio signals or the kind of civilization that might send us messages, but even the most humble, single-celled microorganisms, even bacterial life. The finding would be, without hyperbole, the most transformative scientific discovery in human history. It would tell us that the origin of life is not a unique accident that happened once on a single lucky world in the 4 billion years since Earth formed. It would tell us that life is a natural consequence of chemistry and energy when the conditions are right, or at least that the universe found a way twice in our own cosmic backyard. And, if twice, then the logical implication is that it found a way everywhere that conditions allowed. The universe would be, in that moment, revealed as fundamentally alive in a way that changes everything about how we think about why we are here. The particular importance of Proxima Centauri in this context cannot be overstated. Red dwarf stars are not a curiosity or an exception. They are the dominant type of star in the Milky Way, constituting roughly 75% of all the stars in our galaxy. By the most commonly cited estimates, there are somewhere around 250 billion stars in the Milky Way. That means about 187 billion of them are red dwarfs. Studies suggest that around 40% of red dwarfs host at least one rocky planet in their habitable zones. If that figure is correct, there are something like 75 billion potentially habitable rocky worlds orbiting red dwarfs in our galaxy alone. And because red dwarfs live for unimaginably long times, Proxima Centauri will remain in its current stable phase of hydrogen fusion for another 4 trillion years, roughly 300 times the current age of the universe. Any life that takes hold on a world around a red dwarf has an incomprehensibly vast amount of time in which to evolve, adapt, and potentially develop complexity. To feel the weight of those numbers, try this. 4 trillion years from now, our sun will have exhausted its hydrogen fuel, expanded into a red giant, and destroyed the Earth. The Milky Way and Andromeda will have long since merged. The universe will have expanded to such an extent that all other galaxies will have receded beyond the observable horizon. Most of the stars in the sky tonight will have burned out and gone dark. And Proxima Centauri will still be there, burning its cool red hydrogen unchanged. Whatever evolved on its world during those 4 trillion years, if anything did, would have had more time to develop than we can meaningfully comprehend. This temporal depth is one of the most extraordinary facts about red dwarf systems. The Sun will survive for about another 5 billion years. In that time, complex life on Earth has been present for at most about 600 million years, and technological civilization for perhaps a few thousand. If red dwarfs as planets are viable habitats, evolution there would have not millions but trillions of years to explore the space of biological possibilities. The complexity and diversity of what might arise over such timescales is simply beyond imagination. The flip side of this immense temporal generosity is the stellar activity problem we have discussed at length. Red dwarfs, and Proxima Centauri in particular, are violent stars in their youth and remain active throughout their long lives. The same convective structure that gives them their millennial endurance also drives the magnetic chaos that produces their powerful flares. It is possible, even probable, in the view of some researchers, that most habitable zone planets around red dwarfs are, in fact, not habitable, that the combination of tidal locking, stellar wind bombardment, and UV radiation makes maintaining a life-supporting atmosphere essentially impossible over the long run. But most is not all. The range of initial conditions, the variation in planetary mass, composition, magnetic field strength, volatile inventory, and orbital history is vast, and the universe has proven repeatedly that life on Earth itself has survived conditions that should by straightforward calculation have destroyed it. Life has been found in hydrothermal vents at the bottom of the ocean where sunlight never reaches, and in frozen Antarctic lakes, and in highly acidic volcanic pools, and in conditions of radiation that would kill a human in minutes. The history of astrobiology is to a significant extent the history of scientists being wrong about how hostile an environment has to be before life cannot survive in it. There is also the option of subsurface life. Even if Proxima B's surface has been stripped of its atmosphere and baked or frozen into biological desolation, a subsurface ocean maintained by tidal heating or radioactive decay could potentially harbor microbial ecosystems in the dark, warm water beneath miles of ice. Europa and Enceladus in our own solar system hint at exactly this possibility for icy moons. And if subsurface oceans are a viable niche for life in the outer solar system, they might be viable on a tidally heated rocky world around a flare star too. The universe does not reveal all its habitable niches to telescopes pointed at surfaces from 4 light-years away. There is also a profound philosophical puzzle embedded in this entire discussion, and it is worth sitting with for a moment. We have found a planet around the nearest star. Of all the billions of stars in the Milky Way, Proxima Centauri happens to have a rocky world in its habitable zone, and it happens to be the single closest star to us. Is this a coincidence, or does it tell us something? One interpretation is that planets like Proxima b are genuinely common, that if you pick essentially any red dwarf and look closely enough with precise enough instruments, you will find one. The statistics support this. Somewhere between 20 and 40% of red dwarfs are estimated to host an Earth-like planet in their habitable zone. If the nearest star happens to be one of those, it might simply reflect how ubiquitous such worlds are. The nearest example of a common phenomenon is not surprising. It is expected. The question of whether life exists elsewhere in the universe is not merely a scientific question. It is a question about meaning. If we are alone, if Earth is the only world in the vastness of the cosmos where chemistry ever combined into something that wanted to live, that could perceive, that could ask questions, then our existence is either a cosmic accident of staggering improbability, or the result of some deeper principle we do not yet understand. If we are not alone, if Proxima b, or any of the billions of other candidate worlds we know of, harbors even the simplest forms of life, then we are part of something larger than we have yet imagined. The universe is not empty. It is not silent. It is teeming. James Webb is, in a sense, humanity's most honest attempt to find out which of these pictures is true. Not by looking at Proxima b directly, not yet, but by developing the techniques, the sensitivities, and the conceptual frameworks that will eventually allow us to read the light from small, rocky worlds and learn from it whether an atmosphere is present, whether water cycles through it, whether chemistry there has organized itself into something recognizable. The observations at Alpha Centauri in 2024, the techniques developed for subtracting binary star contamination, the successful detection of carbon dioxide in the atmospheres of distant gas giants, the tantalizing possible biosignature in the atmosphere of K2-18b. All of these are steps along a path whose destination is the answer to the oldest question humanity has ever asked. The universe is approximately 13.8 billion years old. Light from the first galaxies that ever formed has been traveling since before the Sun existed, before Earth existed, before any biology had yet begun to sort itself out from the chemistry of ancient seas. In all of that time and space, the only world we know for certain to have produced life is this one, the one you are resting on right now. And yet there it is, hanging in the constellation Centaurus, invisible to the naked eye, 4 light-years away. A faint red ember of a star with at least 2 worlds in orbit around it. One of those worlds sits in the zone where water could be liquid, where temperatures could be moderate, where chemistry could persist long enough to organize itself into something marvelous. We do not know yet whether it has, but we are building the instruments to find out. We are pointing our greatest telescope at its sun. We are analyzing the light. We are listening. Section 10. Drifting Home, the Philosophical Wonder of Nearby Space. There is something particular about looking at a nearby star, different from the awe we feel when contemplating the remotest galaxies, billions of light-years away. With the distant universe, the scale is simply too immense for emotional traction. We nod at the numbers and try to feel something, but the distances defeat us. But Proxima Centauri is different. It is far enough to be completely unreachable by any current technology, and yet close enough to feel, somehow, personal. When you look at Proxima Centauri, or in the southern hemisphere on a clear night you could, in theory, find it with a modest telescope. You are looking at a star from which any civilization living on Proxima b could, in principle, see our own sun. From Proxima b, our sun would appear as a bright, slightly yellowish star in what to them would be the northern sky. Brighter than any star in our own night sky. Easily visible to the naked eye if they had eyes, the most prominent single point of light in their heavens. They would see it if they were looking. A pale yellow sun burning alone among the thousands of stars of the Milky Way. The thought has a quality of vertigo to it, a slight dizziness that comes from suddenly having to hold 2 perspectives at once. We are looking at them. And from where they are, they might be looking at us. At the same star. The same light, arriving from opposite directions across the same 4 light-years of silent space. The James Webb Space Telescope has not yet given us the image of Proxima b that we ultimately want. The direct image of the planet itself, its atmosphere analyzed, its surface temperature mapped, its chemistry decoded into a verdict on whether something lives there. That image, that answer, likely belongs to the next decade or the one after it, to the extremely large telescope with Ristretto, to the Habitable Worlds Observatory currently in conceptual development at NASA, to whatever instrument humanity invests in next to carry this search forward. But Webb has done something that every great telescope does. It has revealed the difficulty of the question while simultaneously demonstrating that the question is answerable. The 2024 observation of Alpha Centauri A was not a confirmation of a planet. It was a demonstration that this extraordinary machine, with its golden mirror and its patient infrared gaze, can peer into the habitable zones of the nearest stars and detect the faint heat of objects 10,000 times dimmer than the stars themselves. It is a proof of concept for something greater that is coming. In the quiet of wherever you find yourself tonight, let the picture settle around you. There is a small red star, 4.2 light-years away. It has a planet about the size of Earth, orbiting it every 11 days. That planet receives the right amount of energy, in principle, for liquid water. We do not know if it has an atmosphere, but it might. We do not know if it has oceans, but it might. We do not know if anything lives there, but it might. And we are looking. With instruments of almost miraculous sensitivity perched far from the warmth of Earth, collecting photons that have traveled across billions of kilometers of space, we are looking. The search for Proxima B's secrets is one of the great acts of curiosity in human history, an outward reach of the same impulse that led our ancestors to walk over mountain passes and sail beyond the horizon, and wonder what was on the other side. The universe is very old. The universe is very large. And somewhere in the direction of the constellation Centaurus, just barely out of reach, something is orbiting a small red star. We haven't found out what it is yet, but we're getting closer, one observation at a time. Rest now. Let the cosmos be as large as it is. Let the distances be what they are. There is no urgency tonight. The nearest star has been there for 5 billion years, and it will be there still in the morning. If you found this journey worth taking, please consider subscribing to the Science Pillow and leaving a like on this video. It means more than you might think. It helps this channel continue making explorations like this one, and it tells the algorithm that there are people in this world who want to fall asleep with the whole universe in their heads. That feels like a good thing. Thank you for watching. Good night.